be presenting about the life cycle of a star in space. So me and David will be co-presenting. So we're just going to talk about, I guess, which each phase of the star goes through before it finally ends. So it's going to be really interesting, and we're going to compare it to the sun in our solar system. So if the next slide. So this is just our table of contents. We're going to be talking about how a star is like formed right at birth, so in the nebula. Then we're going to go on to like talking about protostars, the T Tauri phase, main sequence stars, red giants, white dwarfs, supernovas, and finally black holes when stars end their life. So this will just show an overall schematic diagram of what we'll be discussing about today when talking about the life cycle of a star. So what is a star? A star is a big ball of gas which gives off both heat and light. A galaxy contains clouds of dust and gas as well as stars, and it is in the origins of dust and gas that stars are born. As more and more of the gas, which is mainly made up of a gas called hydrogen, is pulled together by gravity in a cloud, the cloud starts to spin. As a result, the gas atoms start to bump into each other faster and faster, and then this creates heat energy. And then I can't see like the bottom side, I think it's cut off, but in essence, so the movement of particles ultimately create more, you could say, thermal or heat energy within the star, making it really, really hot. And then afterward, and when we go on the next slide, this causes the star to glow because of all the heat energy, and the glowing cloud gas is now known as a protostar, so the very first or initial stage of star formation. The protostar continues to grow, and once it stops growing, it is known as a main sequence star. Our sun in our solar system right now is a main sequence star, and it can shine for millions of years, but the amount of time that the sequence star lives is determined by its mass, or rather how big it is. So, yes. So, we're going to be talking about nebula next. A nebula is a giant cloud of dust and gas in space, and some nebulae, which ultimately means more than one nebula, come from the gas and dust thrown out by the explosion of a dying star, such as a supernova. Other nebulae are regions where new stars are formed. Nebulae exist in the space between the stars, also known as interstellar space. The closest known nebula to Earth is called the Helix Nebula. It is the remnant of a dying star, possibly one like the Sun. It is approximately 700 light years away from Earth. But how do we know what nebulae look like as humans? Astronomers use very powerful telescopes to take pictures of faraway nebulae. Space telescopes, such as NASA's Spitzer Space Telescope and Hubble Space Telescope, have captured many images of faraway nebulae. So after that, it becomes a protostar. So a protostar is a star, not truly a star until it can fuse hydrogen to helium. Before that, they are called protostars. A protostar is formed as gravity and begins to pull the gases together into a ball. This process is known as accretion. So as gravity pulls the gases closer to the center of the ball, gravitational energy begins to heat them, causing the gases to emit radiation. At first, the radiation simply escapes into a space. However, as the protostar pulls in matter and gets more dense, much of the radiation becomes trapped inside, heating the protostar even more quickly. So, after that is something known as the T Tauri phase. So these stellar or space winds and radiation blow away the surrounding shell of gas and dust, and the third stage, when the surrounding envelope has cleared, is called the T Tauri phase. T Tauri stars, or the class is named after the first star of this type that was so identified, are less than about 10 million years old and provide astronomers with promising candidates or markers in which to study the early lives of stars and planets. So during this phase, a type of disk stops accreting, and the source's radiation comes from the star's photosphere. T Tauri stars produce strong X-rays primarily by what is thought to be coronal activity, much like the coronal activity within our own sun. Although in some cases, a component might be coming from, per se, hot material in the dusty disk around stars.
So, as Prisa mentioned earlier, the star starts to go into the main sequence star, which is the longest cycle of the star life. That the sun is currently in this stage as well. So this young star starts to reach a state called the hydrostatic equilibrium, which is basically a fluid. And this happens because of the gravity compression that is balanced by its outward shape, which gives it the solid sphere shape that we see in our sun as well. So it will spend 90% of its lifetime in this stage, which is quite the majority, and it fuses hydrogen molecules and forms the helium as its core. And so these stars can range from about the 10th of a mass of the sun up to as 200 times as big. So there's a huge range in which this star can be sized. And so Prisa went over this earlier as well, but the length of the star staying in its main sequence stage depends on how big it is. So a higher mass star has more material, so it burns through faster due to a higher core temperature, and it causes greater gravitational forces, and vice versa for the smaller mass stars. So after this main sequence phase, it will go into the red giant phase, which is pretty similar, but this red giant reaches a size of 100 million to 1 billion kilometers in diameter, which is an extreme amount of kilometers. It's a huge size, and since this energy is spread across a larger amount of area, the surface areas are actually cooler, and it reaches only 2,200 to 3,200 degrees Celsius, which is little hotter than the sun. And so this temperature causes stars to shine in the redder part of the spectrum, which is why we call it the red giant, and which is why in the picture it looks red. And so this stage is one of the last stages of a dying star's life cycle, and most of the well-known bright stars are red giants due to their how bright they are and how they're very common. And so these red giant stars also no longer perform nuclear fusion between helium and hydrogen, as mentioned earlier, in their cores, and they heat up and expand several times their previous size. So our sun is, again, at the previous stage, but in order to get to this stage, it will take around 6 billion years. So the sun will then either enter a white dwarf phase or a supernova phase, which I'll mention earlier. But this phase is the less violent phase, and it usually happens for smaller stars. So this will happen when the stars like our sun and other big super red giants run out of fuel, essentially. So they run out of energy, and they'll start to turn into a white dwarf, which is very, very dense. A teaspoon of this white dwarf matter would weigh as much on Earth as an elephant. So this is pretty dense, and a white dwarf's radius is around 1% of our sun's, but the mass is the same. So it's all of that energy that the sun has condensed into 1%, which is very, very small, and making it very, very dense as well. And so from this point on of the white dwarf, it will then turn into a black dwarf, which is the end of this cycle of a star. So This will take tens or even hundreds of billions of years, and then the white dwarf will again continue to cool, and they'll turn into the black dwarf, which is invisible because they're emitting the same temperature as the microwave background as space, so we can't really detect it. And based on the age of our universe, there are no black dwarfs because it takes such an incredibly long time to happen, and our universe is just not that old yet. On the other hand, a big star, right, not a small star, but a huge star will die with a supernova, which is, as you can see in the picture, a huge explosion. And when they explode, they fling their guts into space at speeds of 9,000 to 25,000 miles per second, which is incredibly fast, just showing the sheer amount of power that these supernovas have. And these blasts produce and let go of iron into the universe, which help make both ourselves and the planet. Because as you know, we have iron inside ourselves. So technically, as Neil Tyson puts it, we are made of stardust in a way. And so from this point on, this will become the nebula, and it will restart the new star cycles from the stardust left behind in the explosion, and then these stars will repeat their star cycle. However, from this point on, it can take two paths. It can become a neutron star, or it can become a black hole. So we'll be going over that. So what a neutron star is that it's what happens when a massive star, again, runs out of fuel and collapses. And it's a very central region of the star, and basically it's the core. So it crushes together every proton and electron and a neutron. So if a core of a collapsing star is between 1 and 3 solar masses, these neutron stars can stop the collapse and it will leave behind a neutron star. Since these neutron stars began their existence as stars, they are found scattered throughout the galaxy. You can find them in every part of the universe. And like stars, they can be found by themselves or in binary systems with a companion. So usually neutron stars will be in pairs, and it can rotate and turn into a gamma ray, or it can just be alone. And so these are likely undetectable because they simply just do not emit enough radiation for our technology to identify in space. And a handful of neutron stars actually have been found sitting at the centers of supernovas, quietly emitting X-rays. And sometimes, more oftenly, these neutron stars are found spinning with their companion and will emit a gamma ray burst, which is essentially the most powerful burst in the universe, and it'll shine 2 rays of light in both directions, which can absolutely anything in its path. And so from this point on, it'll become a black hole. You guys probably know what black holes are, but they're the end of the supernova phase of a star cycle, and they basically pull everything around them into them. They're basically massive amounts of mass in a very small space, and they have strong enough gravity to pull in light, which is why we call it the black hole. To put this into perspective, to make a black hole out of the size of the Earth, if you put the Earth into a black hole, the entire planet would need to be squeezed down to the size of a pea, which is very, very small compared to the size of our Earth. That's just how dense it is. These black holes can slow down time, in fact, and rip you apart, and nothing can escape the grasp of a black hole when it reaches its event horizon. So it basically destroys everything in its path and everything that it takes in. Some researchers think that black holes actually help create the elements because they break down matter into subatomic particles, which is basically the base building blocks of everything that we know today. And so
And
here on the right, we can see a picture of a black hole.
And also, in fact, if you look on the previous slide, the picture, that is, oh no, for black holes. If you look on the picture on the right, that is a picture captured just last year from, I think, just a graduate student who developed a type of code, long, extensive code, to actually visualize what a black hole looks like. In fact, I know a lot of you guys have heard of black holes, but we've never actually, it's only been theoretically hypothesized from Albert Einstein. So with the showing, ultimately, with her code, we're now able to actually see visual proof of what black holes do exist. And another interesting fact is, if a black hole were to actually come towards Earth, a lot of people would just think we'd be sucked in like right away. As David mentioned, that wouldn't really happen, and here's why. In fact, we would actually start floating like really slowly. So like everything would just start floating super slowly until you just go up and up and up and up in space until you reach the event horizon. And it's really crazy. And you can watch some simulation videos because of how distorted things become. Once you reach the event horizon, right, light can't even escape black holes. So like your vision would be so distorted in essence, and you would go super fast into the black hole. And scientists still don't know, if you were to go in a black hole, where would it take you? Some physicists think that it's kind of like a loophole, that when you go in a black hole, you might, after being like, you know, broken into subatomic particles, you might end up somewhere else in the universe, but we still don't know. So that's an interesting mystery as to what black holes are. But yeah.
Yeah. So I have a video for you guys. Let's hope this works. Can you guys hear that?
In today's video, we're going to look at the life cycle of stars.
I can hear it.
It all starts.
Volume higher. Oh, David, I want to.
Okay, what?
You make the volume higher.
In today's video, we're going to look at the life cycle of stars. It all starts with a big cloud of dust and gas, which we call a nebula. Over time, the attractive force of gravity pulls the dust and gas together to form a structure called a protostar. And as more and more particles collide and join the protostar, it gets bigger and bigger. And so its force of gravity gets even stronger, which allows it to attract ever more dust and gas. The gravity also squeezes the protostar itself, making it more and more dense. This means that the particles inside it collide with each other more often, which in turn raises the temperature of the protostar. Then, when the temperature and pressure get high enough, hydrogen nuclei start to fuse together to form helium nuclei in a process called nuclear fusion. This gives out huge amounts of energy, which keeps the core of the star hot. And it's at this point that we call it an actual star, or more precisely, a main sequence. While it's a main sequence star, the outward pressure caused by all of that energy that's being released by nuclear fusion is perfectly balanced by the inward pressure caused by gravity. This allows for a long, stable period that can last for billions of years, and it's this stage that our sun is currently in. At some point, though, the star will start to run out of hydrogen, which, remember, is effectively its fuel. You don't need to worry about the details, but basically this means that the star won't be able to do any more nuclear fusion. And so the inward pressure of gravity takes over and contracts the star into a small ball until it's so hot and dense that nuclear fusion can start up again, which will cause it to expand again. This time though, instead of just forming helium, the nuclear fusion will form heavier elements, including all the elements up to iron on the periodic table. Exactly how much the star expands depends on how big the initial star was. If it was a small to medium star, like our Sun, then it will form a red giant. But if it was a big star, then it would form a red supergiant, complete the rest of their life cycles in different ways. So we're going to take a look at the red giant first, and then we'll come back to the red supergiant. After a relatively short time, the red giant becomes a and expels its outer layers of dust and gas. This leaves behind a hot, dense, solid core, which doesn't do any nuclear fusion. We call this a white dwarf because it gives off lots of light, so it appears white, and is relatively small. Over time, the white dwarf gets cooler and darker, until finally it transitions to a black dwarf, because it no longer has enough energy to emit light, and so appears dark. Now, if we whisk back to the two options for our main sequence star, the other possibility for the really big stars was to turn into a red supergiant. So let's now look at these. Red supergiants actually start to shine brightly again as they undergo. After passing through several cycles of expansion and contraction, they eventually explode in something called a supernova, which forms elements even heavier than iron that get ejected all across the universe. What happens next, again, depends on how big the star was. If it was just very big, then it will condense into a very dense core called a neutron star. However, if the star was absolutely massive, then it might collapse in on itself and become a black hole. The reason we call them black holes is because they're so dense that their gravity is able to pull in any light that passes nearby, which means that they literally appear as empty spaces or tiny holes in the universe where no light is ever emitted. So to quickly recap everything, stars initially form from clouds of dust and gas that slowly come together under the attractive force of gravity to form a protostar. When the pressure and temperature get high enough, nuclear fusion takes off, and we transition to a main sequence star. After a long time, often billions of years, the star exhausts its hydrogen supplies and becomes either a red giant if it's a small to medium size, or a red supergiant if it's a big star. The red giants throw off their outer layers to reveal a hot, dense core that we call a white dwarf, which then cools to become a black dwarf. Meanwhile, the red supernova, ejecting heavy elements across the universe. And it then condenses into a neutron star if it was only pretty big, or into a black hole if it was truly massive.
Yeah, so that's the end of our video. Okay, so I think Prisa has a Kahoot for us.
Wait, before you go to the Kahoot, can you keep it on the slide really quickly? I want to show them the diagram. So we didn't exactly make a individual slide for super red giants, but just to clarify, small, medium, or main sequence stars have the option of turning into red giants, and then if the heat energy is really like big and they end up being super big stars, then they're going to be a super giant. As a result, since they're extremely big, the super giant blows up, if you can kind of think of it, which is known as a supernova. And after that, basically, it then becomes either a neutron star, right, which we discussed, or a black hole. Meanwhile, like small medium stars, since they're not as you would say dense or in big, they would just become white dwarfs, which is like the birth of a new star, and then a black dwarf, which we didn't really emphasize at the end. But Yeah, so that's just a type of true schematic as to how small, medium, and then super large stars would differ in terms of their fate of their life cycle. But yes, so just as a quick clarification. And David is right. I have a Kahoot, and I know we don't have many people in the chat. I apologize. I forgot to send our weekly email notifying everyone for our Zoom session link, but it's okay. We can still play with 6 or 4. So I will be sharing my Kahoot. So I'm going to just do it in classic mode. So please kindly log on to Kahoot. The link, if just www.kahoot.it, and the game pin is 318085. I'll put it in the chat box. So, link is to log on is www.kahoot.it. And then code, access code, or how would I say it? The game pin, my bad, is 318085, sorry. 318085. So I put it in the chat box for everyone on their laptops. So I would recommend opening Kahoot in a new tab. And the thing is, it's kind of tricky since we're doing this virtually. I will be sharing my screen. So if some, so can everyone see my Kahoot screen?
Yeah.
Yeah.
So I think we're just waiting on 2 people. And then Sanya, or sorry, Sanaya, I think, great.
Yeah,
So,
I just
perfect. Great. So we have everyone in. Again, it's not a super big crowd, but you know what, we'll still have fun. So basically so this is, since we're doing this virtually, in order to play the Kahoot, you have to read the question off the screen, the Zoom session screen, and then you have to answer on your screen, if that makes sense. So we'll start. So good luck, everyone. Kahoot for Star Life Cycle presentation. So does fusion only occur in the core of a star? Triangle, true, or diamond, false? And this Kahoot is a little tricky. I went for like small snippets within the slide presentation, so that's why. So yes, good job. Majority of you got this right. Fusion only occurs at the core of the star. And what do we remember? It's called nuclear fusion, where hydrogen atoms ultimately become helium. So good job, everyone. You got it right. So, good job, Shannon, for being number 1. But yeah. What is the last life stage of a low mass star? We kind of discussed it in the video, and I made a differentiation as to how it differs from a high mass star. And yeah, triangle, red dwarf, diamond, white dwarf, circle, black hole. Okay, good job. A majority of you got this correct. Technically, you could correct me and say, hey, Parisa, technically the video said a black dwarf, which is true. A black dwarf in essence is just a dormant white dwarf, but the last technically known stage of a low mass star is a white dwarf. But if you guys remember, the last stage of a high mass star, right, like supergiants, is a black hole or neutron star. So a majority of you got this right. Oh, so good job, Camden, Henrico 4H, and Sanaya. Good job. So next question is, do low mass stars have less or more gravity than high mass stars? So this, you can kind of, I guess, use your reasoning. Good job, everyone got this correct. Yes, high mass stars, since they have a bigger radius, thus have a higher gravitational force. It's just like planets. The bigger something is, the more gravitational force it has. So good job, that everyone got that correct. So how hot is a white dwarf? We discussed this in, I think, the slide. There is a sentence. Triangle 1 million Kelvin, diamond 10 million Kelvin, 500,000 Kelvin, or square 100,000 Kelvin. So how hot is a white dwarf? Oh wow, this is so funny. I guess one person put their answer in each of the options, but it's actually 100,000 Kelvin. That's how hot a white dwarf is. 1 million Kelvin would be, because it's like higher than Celsius, so yeah. But 100,000 Kelvin is the accurate temperature of a white dwarf. So whoever got that correct, oh, David, good job. Everyone put an answer of each option on there, so that's good for you. So this is a multi-select question. End stages of a high mass star. So think of like what I said with the high mass star. A triangle superhole, a diamond black hole, circle red dwarf, or a square neutron star. So yes, a lot of you got this correct. Good job. Wait, actually, well, black hole and neutron star, I didn't really emphasize it in the presentation, but it's something also termed as a superhole, is the end stage of a high mass star as well, which can be synonymous to black hole in some instances. But the majority of you picked the obvious options. But red dwarf is not the end stage of a high mass star. Red dwarf is a small medium star right before it either becomes a red giant or a red supergiant. So, but a majority of you got this correct, so that's good. Good job, Camden, and good job, David and Sanaya. You guys are in the lead. So, in how many years will the sun be a red giant? I think I put this in the presentation. Hint, our sun is a main sequence star right now. So if it's a main sequence star, how long will it be until it becomes a red giant? Okay, so again, a lot of you put an answer for each option, which is kind of interesting, but it will be 6 billion years. So our sun's predicted to be to last 6 billion years until it finally becomes a red giant. Right now it's a main sequence star. So this is quick information. So good job, David, for getting that correct. That was tricky. So what is a glowing cloud gas also referred to as? It was in the presentation. This might be an easy question. Think about how stars are formed. Right? So good job. A lot of you got this correct. It is protostar. That's what it's referred to when a star is glowing, right? Because when a star is formed, there's a lot of heat energy occurring, causing it to actually like glow. And it has the gas, a lot of gas still surrounding it. So the nickname for glowing cloud gas is basically also referred to protostars. Not supergiants, although I can see how that might be a tricky option. So good job, everyone who got that correct. So in question 8, what causes the formation of protostars? We mentioned this in PowerPoint. Triangle hydrostatic equilibrium or diamond accretion. So actually, it's not hydrostatic equilibrium. It is known by a process called accretion. It was briefly mentioned in the PowerPoint. So for accretion, ultimately, what occurs is that during the accretion process, a protostar is formed as gravity begins to pull the gases together in a ball. So that process in itself is known as accretion. But the hydrostatic equilibrium is actually just a state. So in hydrostatic equilibrium, that mainly occurs with main sequence stars, not protostars. So ultimately with the main sequence star, this young star reaches the hydrostatic equilibrium state, which ultimately refers to a condition of fluid at rest. So it reaches this hydrostatic equilibrium state, a main sequence star, because its gravity compression is balanced by its outward shape, giving it a solid shape. So accretion really goes with protostars, and hydrostatic equilibrium is a state that goes with main sequence stars. So that was a tricky question, clearly, but it's all right. After what life cycle stage do high and low mass stars differ in what they become? We kind of discussed this in the video. You saw at the very end the diagram. After what stage do high and low masses differ? Hint, think of the color. So I think you guys kind of knew the answer, but maybe didn't read the question carefully. It says, after what life cycle stage does it occur? So it's actually after red giant stage. Because right after, if there's a red giant, it can either continue on being a red giant or then being a supergiant or red supergiant. As a result, right, as discussed in the diagram, the red dwarf, when it becomes a red giant, will then either become a white dwarf and then a black dwarf, while the supergiant will become super like dense and then either become a black hole or a neutron star. But it's after the red giant phase then really it will either go into being a white dwarf, or if it becomes big, right, if it keeps accumulating more heat energy, then it'll become a supergiant. So that was a tricky question, but overall, a lot of you guys are still doing. So what causes a supernova? I think this was in the presentation. Think about when a supernova occurs. I mentioned this in the diagram of the last slide. Does it occur with low mass or high mass stars? So when you know that, and think about what will occur. So good job, everyone. Yes, a supernova occurs when a high mass star is running out of nuclear fuel, right? So a high mass star refers to supergiants, right? Low mass stars are like just normal red giants after red dwarf stage. So yes, it occurs when a high mass star begins running out of nuclear fuel. So good job, Camden, for back in first place and beating David. That's really impressive. And Sanaya for being right behind. So good job, everyone. What type of star creates a planetary nebula? So over here, kind of think about the lifespan of the star, right? And then the planetary nebula, in essence, so a planetary nebula is basically a ring tube nebula formed by an expanding shell of gas around an aging star. So it's kind of this new nebula formed once a star is like really old or has aged. So that gives a hint of any sort. So I kind of mentioned that hint. It was a bit late, but in essence, since it's an aging star, that should kind of let you know, okay, it can't be red giant. So now you're deliberating between black hole, neutron star, and white dwarf. As we discussed earlier, neutron stars and black holes are the end stages or the end of the life cycles for high mass stars like supergiants. However, white dwarfs are the end stages for low mass stars like just red giants. So ultimately, a white dwarf is ultimately the end stage of a low mass star, which will lead to planetary nebulas. You can also use like reasoning and say, okay, right, if there's a black hole or a neutron star, which is formed after like these huge, densely populated supergiants, it will probably not create a planetary nebula. It will, because the gravity is so huge, right? Like there won't be a nebula surrounding a black hole. So you can kind of, okay, it has to be then a white dwarf, which is the end stage of a small, medium-sized star. That was a tricky question, but we'll see about the future questions. So can we see black holes? This question actually, don't take it too in depth because the answer can be both in essence, but yeah. So yeah, the answer is now yes, we can now see black holes, right? Because as we saw that picture, a graduate MIT student just basically developed a code where we can actually visualize black holes through telescopes. ultimately proved Einstein's prediction or hypothesis that black holes do exist in our universe. So we can now see black holes through telescopes. So that was a tricky question, but good job, Sanaya and Henrico 4H for getting that correct. So tricky question. This wasn't in the presentation, but how much of a star's mass is equal to the core? This isn't in the presentation, but kind of just think about the first question in this Kahoot. Where does the most amount of nuclear fusion happen? At the core. So then I think about, wow, if the most amount of fusion occurs at the core, then it must be a lot of percentage of the mass. So good. A lot of you guys kind of used your best to 90%, which is perfect because if you remember the first question of our Kahoot, most of the nuclear fusion, right, of hydrogen atoms becoming helium atoms, which ultimately sustains the sun, or sorry, sustains the star, occurs at the star's core. So since a majority of the nuclear fusion, which creates, you could say, new and the star occurs at the core, you can kind of guess and say, okay, then a bunch of the star's mass has to, a large percentage of the star's core, since nuclear fusion occurs there. So yes, it's 90%. It wasn't in the point, but it was a tricky question. So good job, everyone who got that correct. So what two particles does neutron need to make neutrons in general? It was in the PowerPoint. There are these two subatomic particles: triangle, positrons and electrons; diamond, neutrinos and electrons; circle, protons plus electrons; or square, positrons plus neutrinos. One of these options was only in the presentation. So good job, everyone. Answer is protons and electrons, right? So kind of just think about it simply. Protons have a charge of +1, electrons also have a charge of -1. So +1 and -1 added together is just 0, meaning no net charge, and that ultimately is what a neutron has. There's no necessary charge to it. It's a subatomic particle. But yes, it relies on protons and electrons. All the other particles are just kind of dark matter particles that, you know, are not really related. It's more complex physics, but yeah. So good job, everyone who got that correct. That was a tricky question because it was, I think, only repeated once in the presentation. So finally, a white dwarf cannot create internal pressure. True or false? So a lot of you got this correct. Good job. So in essence, a white dwarf, 1 second, this happened to my screen. It can't really create internal pressure, so it relies on gravity to ultimately help pressurize the star into either becoming a black dwarf, right? Dormant, but yeah, that's ultimately what happens. A white dwarf in itself cannot create internal pressure, so it depends on the gravitational force, external gravitational force. So I can probably elaborate more on that right now, but oh, okay, it's not there, but okay, but never mind. So that was just the Kahoot. So in third place, we have Henrico 4H. I don't know if that was Kendra or Carter, so good job. Second place, we have Camden. And first place, we have David, which honestly, Camden and Henrico 4H, you should be really proud because David made this presentation. So the fact that he won is not surprising, but you guys did really well. But you guys did truly Kahoot. So I'm so glad that you guys answered the majority of questions correct. And also good job, Sanaya. You were also pretty close. And yeah, so I hope you guys learned about star formation. It's a really kind of, not want to say complex, but not a super well-studied topic. And in essence, we just wanted to kind of tell you about how stars are formed and their different life cycles. But this is just a fundamental guide as to what David and I presented to you guys today. Like, there's so much to learn. Like, you can read about HR diagrams correlating about the star's mass to how long it will last. And HR diagrams can help give you these plots which visualize if a star is a type of main sequence star, red giant star, supergiant. But I hope you guys learned a lot because stars don't actually have one direct path. For example, as you saw with red giants, which are low or medium mass, stars with low or medium mass, they can ultimately become red. After they become red giants, they can then become white dwarfs and then black dwarfs and create planetary nebula. Like our current sun in the solar system, it was formed actually initially as a white dwarf, right? And then it became a cycle and then became a main sequence star. But for really super dense populated stars and big stars like supergiants, right? Stars with a high mass, it won't become a white dwarf. It will actually then become, as we mentioned earlier, a neutron star or a black hole, which would make sense. So you can't really create a solar system directly in the black hole, otherwise it would kind of get sucked in the black hole. But yeah, I hope you guys learned a lot. This kind of deviated from a lot of our typical STEM-based learning sessions like curriculum. So I just find it to be a little interesting. But yeah, so yeah, I'm glad you guys learned something. We ended a bit earlier today, but I think Carter mentioned that she had another session at 12 o'clock. Carter, if you want to explain, maybe they can hop onto the next session.
We actually have a 4-H session for the agents at 12, but we do have our, no, that's okay, but we do have our academy session today at 1, and we're going to be talking about how you can do some fun experiments with eggs, and so we are going to be doing that one. Let me see if I can find the link real quick, or Kendra, if you've already got it.
Okay, so as Kendra and Carter said, they're going to have another session at 1 o'clock today. So I really recommend you check out. They have a lot of other fun activities at 4-H. And then finally, I apologize. Our session usually wasn't as big this week. Usually we have like 10 to 12 participants. I personally forgot to send the weekly email. So a lot of people forgot that they were supposed to click on this link for the Zoom session for Train Your Brain. But I highly recommend you guys to join our next Zoom session. One of our other STEM8 members will be presenting. And I promise there'll be